Okay, hello and welcome back again to this 29th lecture of Bio Microelectromechanical Systems. Let us quickly review what we did in the previous lecture. We talked about some of the steps towards derivation of the first Navier-Stokes conservation of momentum equation, and basically we discussed how we can represent the acceleration of a particle in at a point P, in a velocity field V defined or varying with respect to the position, coordinates and time. We also talked about how angular velocity of a certain particle essentially can be related to the average velocity of both sides of a control volume, and we investigated the rotation case and the angular deformation case and found out that they can be represented as the variation of the y velocity in the x direction and the x velocity in the y direction respectively. And we talked about these different kind of deformations that a control volume, a cubic control volume would have, including translation, rotation, angular deformation and linear deformation as the control volume moves along the path of fluid in a medium, in a certain medium. So today let us just go ahead and try to complete what we left unfinished of the conservation of momentum equation. We got the several force components in the x, y and z direction respectively as the equations dfx equals dfbx, which is the body force in the x direction, times the force due to stress in the x direction, and we represent this as rho gx plus delta sigma xx by delta x plus delta tau yx by delta y plus delta tau zx by delta z. Similarly dfy and dfz respectively dfby plus dfsy, which is rho gy plus delta tau xy by del x plus delta sigma yy by del y plus delta sig tau zy by delta z. Similarly dfz is the body force in the z direction plus the force due to stress in the z direction, which is equal to rho gz plus delta tau xz by dx plus delta tau yx by dy plus delta sigma zz by dz times of dx dy dz. Actually the volume element is multiplied everywhere, so this is also the same into dx dy dz. This is also the same times of dx dy dz respectively. So from the Newton's second law, if you consider this control volume, that really df, the amount of force that the control volume would actually try to incorporate or face, is nothing but m, the mass of the control volume, or delta m times of dv by dt, where v is the velocity of the particle at a point P, and it changes to vx plus dx, y plus dy, z plus dz at time instance t plus delta t respectively. We did this derivation, as a matter of fact, just before we started considering the stresses in the control volume when we talked about acceleration. So therefore in this particular case you can represent really this as m d velocity vector with respect to time, which is nothing but rho dx dy dz, which is the elemental volume, rho being the density. We assume rho not to vary with t, or it's essentially an incompressible case. So times of u del v by del x plus v del v by del y plus w del v by del z plus del v by del t. Okay, and if you actually physically resolve the different components dfx, dfy and dfz in this particular expression, then you are left with dfx vector is essentially rho dx dy dz times of u del u by del x plus v del u by del y plus w del u by del z plus del u by del t, and let us call this equation 1. Similarly, del Fy, the total amount of force is rho dx dy dz times of u del v by del x v del v by del y plus w del v by del z plus del v by del t, where u, v and w are basically components of velocity vector v vector in the x, y and z direction. And similarly, df z vector is essentially rho dx dy dz times of u del w by del x plus v del w by del y plus w del w by del z plus del w by del t. Okay, so that is equation number 3. So you have these 3 equations as respectively dfx, dfy and dfz, and we compare these to the forces obtained earlier. So comparing 1, 2 and 3 with the forces which we got in the earlier equations, okay, which equates the body force and the force due to the stress. So basically, if you compare this, the new set of equations which come out because of that would be essentially rho times gx plus del sigma xx by del x plus del tau yx by del y plus del tau zx by del z times of dx dy dz essentially equal to rho dx dy dz times of u del u by del x plus v del u by del y plus w del u by del z plus del u by del t. Now this time variation, the time component with respect to time, is a separate entity altogether, as you are seeing here, as we made in the first assumption before. So these elemental volumes kind of cancel each other and we are left with straight equations rho gx plus del sigma xx by del x plus del tau yx by del y plus del tau zx by del z is equal to rho times of u del u by del x plus v del u by del y plus w del u by del z plus del u by del t. Okay, so that is what the x balance would be between the m ax, that means the force in the x direction, and the force due to the body force or the stress in the particular control volume in question. Similarly, we will do the same kind of analysis in the y direction, the z directions respectively. So the 2 equations that we get as a result of it, I am just writing down. So this, let this be equation 4. So similarly, we have equation 5th in the y direction as a comparison between all y forces as rho gy plus del tau xy by del x plus del sigma yy by del y plus del tau zy by del z equals rho times of del v by del t plus u del v by del x plus v del v by del y plus w del v by del z. This is equation 5. Similarly, in the z direction we have an identical result where rho gz plus del tau xz by del x plus del tau yz by del y plus del sigma zz by del z is nothing but rho times of del w by del t plus u del w by del x plus v del w by del y plus w del w by del z respectively. So this is equation 6. So if you consider the values of the different shear stresses tau xy, tau yx, similarly tau zx and tau xz and tau yz and tau zy respectively, in terms of its respective variations of the velocity components with respect to space components as we derived in case of rotation and angular deformation before, we will be left with a very simplified and straightforward equation. So let us say, as we have done before, tau Ix and tau xy causing angular deformation can also be expressed as minus mu, let us say d gamma by dt, right, which is equal to mu times of del v by del x plus del u by del y. And similarly tau yz equal to tau zx zy is same as mu times of del w by del y plus del v by del z, right. And similarly tau zx equals tau xc, and this we did actually in the last class or last lecture, how this derivation happens again, du by del z plus del w by del x respectively, okay. And there are some other approximations that we need to make here, which comes from thermodynamic pressure, the relationship between the thermodynamic pressure, the stress components, be it shear or be it principal stress, and the velocity. So all these three linked together, and I am not going to actually derive these pressure stress equations separately. It is an altogether separate topic, but I am going to assume the approximations which are made in terms of relationships between the different stresses and the pressure, etc., and then try to put this back into the equation in question and try to figure out what the final form of the Navier-Stokes momentum equations, conservation of momentum equations would look like, okay. So there are definitely relationships between local thermodynamic parameters like pressure, sigma ii, this is linear stress, and velocity, okay, at point O, around which this control volume has been indicated. If you may remember, we indicated the control volume by defining a central location O, on both sides of which the control volume extends dx by 2, dy by 2 and dz by 2 respectively, with a plus and minus sign both. So here the relationships that come based on this argument are sigma xx equal to minus p, p is the thermodynamic pressure, minus 2 by 3 mu del dot v, v again is nothing but ui plus vj plus wk, okay, plus twice mu del u by del x, okay. Similarly you have sigma yy equals minus p minus 2 by 3 mu del dot v plus twice mu del v by del y, and sigma zz equals minus p minus 2 by 3 mu del dot v plus twice mu, give me a minute here, twice mu del w by del z. Mind you, this mu is essentially the viscosity, okay, relationship between the shear stress and the velocity gradient with respect to the perpendicular direction, the direction of flow, and the del v of course is essentially nothing but again ratio between du by dx plus del v by del y plus del z by del x or del w by del z respectively. So these relationships, if we assume them and we do not derive them and then put this back along with the stress vectors that we have seen before, the shear stress vectors here in equations let us say 7, 8 and 9, we finally get a form of the Navier-Stokes equations which really is something that under the incompressible flow conditions are assumed to be true, okay. So the final form again, so I am going to write from here by substitution of these shear stresses and the relationships between the different principal stresses. Let us call this equations 10, 11 and 12 respectively. Okay. So, what was our earlier relation? Our earlier relation was between the m dV by dt and the forces due to the stress components which came into being, and here the relationship was really rho times of d by dt of u. So, basically this du by dt here though is an operator which we have designed in a very particular and a peculiar manner. So, as you know here, the left side of the equation already was rho times of u del u by del x plus v del u by del y plus w del u by del z plus del u by del t, right. So, we take this to be the operator d by dt of u, okay, u being this variable here. Essentially the other format, the operator d by dt is nothing but u del by del x plus v del by del y plus w del by del z plus del by del t. That is essentially what the operator is. So, we have defined this operator in this manner. So, the left side becomes rho du by dt, and the right side of this equation, as we already know from previous examples, becomes rho gx plus del by del x of sigma xx, and sigma xx, as you already know, comes from the pressure equation as minus p minus 2 by 3 mu del dot v plus twice mu del u by del x. Okay, that is what sigma xx is. So, d by dx of sigma xx plus del by del y of the equation was tau yx, which can be represented as from the angular deformation equation mu times du by del u by del y plus del v by del x, and plus we had d by dz of tau zx, which can again be defined from the angular deformation equation as mu times del w by del x plus del u by del z respectively. So, this is equated in general to rho du by dt, whereas I told you this essentially is an operator. Okay, that is how you represent this equation. So, if you solve this whole equation here on the right hand side, and this is of course the LHS, this is the RHS, okay, of the equation. So, you are left with more, particularly for incompressible flow, if you assume the density is really constant, okay, you are left with a probably more appropriate form of equation, which is more like rho times of the operator d by dt of u is essentially equal to rho gx minus del p by del x, okay, and plus you are left with mu times of del 2 u by del x 2 plus del 2 u by del y 2 plus del 2 u by del z 2 respectively. So, this is in the x direction really, and this again, as you know, is nothing but rho times of del u by del t plus u del u by del x plus v del u by del y plus w del u by del z. That is what the del operator or the d operator here, d by dt, really is. So, in a nutshell, the Navier-Stokes equations then in all three dimensions, all three directions x, y, z, can be written as rho times of del u by del t plus u del u by del x plus v del u by del y plus w del u by del z equals rho gx minus del p by del x plus mu del 2 u by del x square plus del 2 u by del y square plus del 2 u by del z square. That is let us say equation A in the x direction. Similarly, you have rho del v by del t plus u del v by del x plus v del v by del y plus w del v by del z equals rho gy minus del p by del y now, and plus you have mu times of del 2 v by del x2 plus del 2 v by del y2 plus del 2 v by del z2, and similarly this let us call as B equation in the y direction, and in the c in the z direction we call this equation C. So del w by del t plus u times of del w by del x plus v times of del w by del y plus w times of del w by del z is equal to rho gz minus del p by del z plus mu times of del 2 w by del x square plus del 2 w by del y square plus del 2 w by del z square respectively, and this we call as equation C. Okay. So these are really the three directions of the conservation of momentum equation, Navier-Stokes second equation, as you can see. I would like to further kind of try to notate the two equations that we have formulated so far in terms of the conservation of mass and the conservation of momentum in terms of i's and j's. So this is a kind of generic notation which can be used and extended to all the three dimensions, but then essentially the notational representation makes the equation look much more compressed, and so would essentially do a dimensional analysis on this these equations probably in the next slide, where we will see that if I can translate the scale in question where these equations are executed to the micron level, what is going to happen to both the conservation of mass and conservation of momentum equation. So therefore I would like to represent these equations, these all three equations, by a notation, and before that let us actually write the conservation of mass again. So conservation of mass, as you know, here is del u by del x plus del v by del y plus del w by del z equal to 0 for an incompressible flow essentially, and therefore this I can notate in a little more appropriate manner as del ui by del xi equals 0. We assume that i's essentially are all the i's essentially are all the so therefore as you see here notationally the I represents, or I varies between 1, 2, 3 would represent u, v and w, right, and x, y and z. So this is a very straightforward equation that del u I by del xi, that means del u by del x, del v by del y, del w by del z summation is equal to 0. Okay. So this is a notational representation of the conservation of mass equation. It's the first Navier-Stokes equation. All right. The other equation that we derived just about last slide can be notated as del, or let us actually do it here and then translate back the information. So what is this equation really? If you see here, there is a u component in all these operators in equation A. Similarly there is a v component in all these operators in equation B, and similarly a w component in C. Okay. And what is interesting also is that the x, y, z are varying in each of these equations. All right. So if I notate all these u's, v's and w's as I, that means I varies in the direction of the rows, okay, and j varies in the direction of the columns, okay, as if j is varying in the direction of the columns. So I can notate this equation in a more appropriate manner as rho times of del ui by del t, okay, plus uj. Now as you see here, u, v, w are varying in the j direction. So j varying between 1, 2 and 3, meaning these u, this v and this w is actually corresponding to the j. So uj times of delta ui by delta xj. Okay. So essentially again as you see, the j is varying wherever there is a variation in the columnar direction, it is j, wherever there is a variation in the row wise manner it is I. That is how you are subscripting both the variables. So, that is equal to rho times of f I, again I varies in the columnar direction, this is g x, this is g y, this is g z, all these in the columnar in the row time in the row direction. So, f I minus del p, and let me just quickly delete this right here, let us mark C here. Okay. So, this is C. So, this is del p over del xi. Again, as you see here, in case of p, the subscript here varies in a row wise direction, in row wise manner. So, that is I plus neta, and essentially here you have plus neta times of del 2, and you have a variation of u here, as you see u, then v, then w is in the row wise direction. So, this is corresponding to I. So, del 2 u I, and you have in the denominator here del x j 2, because x y z, as you are seeing here, is varying more in the columnar direction. So, that is what the representational, the notational representation of this particular 3 directional momentum equation of Navier-Stokes is really like. So, we can write as rho del u I by del t plus u j del u j by del x j, okay, equals rho f I. F I is actually a representation of the body force or G, minus del pressure P by del x I plus eta, the viscosity, del 2 u I by del x j 2. That is how you represent the conservation of momentum equation. Now, there is also a third equation for conservation of energy. But essentially it contains a temperature term, that is the only difference that this particular equation has, and so therefore as in this particular scale we consider in the microscopic, particularly surface domain, our flows are mostly dominated by the prominence of the surface over the volume, right, and there are effectively not much change in the viscosity and the density. We still assume continuum based properties at this particular scale, the micron scale at least, and so therefore there are no variations in these properties with temperature. Okay. So therefore really the energy equation is not needed as far as the micro scale flows are concerned. What I would be more worried about at this stage is that how we can scale down the momentum equation. So in the scaling equation we have to assume the following presumptions. Okay. Now, number one is that all flows are low Reynolds number flows. Okay. So why we actually try to take a low Reynolds number flow is that a great many microfluidic devices operate in regimes where the flow moves slowly, that is number one, and number two in small dimensions. Okay, that is number two. Say for instance you are talking about a very thin piece of channel or a very thin size of the micro channel which is defined by photolithography. So there the channel thickness is defined by the film thickness, and the film thickness could be anywhere between, let us say, 20 microns all the way to about 100 microns or so. Now 100 microns is effectively the diameter of a human hair. Okay. So you can consider that what is the what is the effective volume through which this flow would actually flow. And it is very obvious to assume that the flow rates typically would be a few microliters per minute. That means the volume discharge through this thin sample is really low, and so you are packing the molecules in a smaller volume, and plus secondly moving them in a very slow manner, which is constrained by the geometry, and therefore most of the cases the flows are typically laminar in nature, and low Reynolds number is an obvious conclusion out of all this, because Reynolds number is nothing but rho Vd by mu, where velocity v or this dimension d, length dimension d, whichever is smaller, makes the overall Reynolds number very small. So effectively we really need to determine whether the flow happens slowly relative to the length scale that we are considering, right. And so therefore we really need to scale down the original dimensional variables in the earlier two equations, okay, the conservation of mass and conservation of momentum. Okay. So one of the reasons why dimensionalization, non-dimensionalization is preferred at these and many other applications is because scaling down will ensure that you do not have any absolute physical parameters like density, viscosity, then length scale, time scale, etc. So what you instead have is a ratio, and the ratio is comparative to a certain feature size or a certain parameter size, which is generally prevalent at the scale at which you are non-dimensionalizing the particular equation. So this is a method which is used, be it Lennard-Jones potential, be it microfluidics, be it MD simulations, just to ascertain that you are essentially using dimensional variable, non-dimensional variables at the scale that your experiments are all supposed to be. So the equation would be a good estimate of that particular scale when instead of a dimensional form you use it in a non-dimensionalized way compared to or in comparison to parameters at the particular scale of the experiment. So therefore in this particular case also, how do we do that? We first of all find out what are the variables which are effectively there in all the Navier-Stokes equations. So you have velocity u as one variable, space coordinate x, y, z, whatever you call. So this is the length variable, so there is a time variable, and then there is a pressure variable p, and so therefore we need to ascertain some characteristic values of these parameters at the micron scale, okay, for non-dimensionalization. So essentially let us consider a geometry. Okay, so we now consider a geometry whose characteristic length is let us suppose d, and whose characteristic velocity is u, okay. So we represent everything in terms of d and u, time scale automatically follows suit, and as we will see the density and the pressure etc. will also be represented in terms of all these quantities, okay. So essentially that is what we will be trying to scale down, and we make these non-dimensional numbers and call them with a or notate them with a subscript star like xi star, ui star, so on and so forth. So, basically now if you look at let us say the scaling. So, we consider a geometry whose characteristic size is represented, just give me a minute here, is represented by the quantity xi, okay, sorry, the quantity d. So, it is represented by the quantity d. Similarly, the average velocity is represented by u here, okay. So, average velocity at that scale is represented by u, okay. So, therefore, this number xi star, which is actually a dimensional, non-dimensional number, is exactly equal to xi by d, and similarly ui star, the non-dimensional velocity number, is equal to ui by u, okay. So, therefore, that is how you represent these dimensionless numbers, and the idea is to convert the Navier-Stokes equations, both the mass as well as the momentum conservation equations, into these quantities with subscript stars, so that the equation is kind of a scale down model into the micro scale for applications. So, now from these two equations we can further derive that xi definitely can be represented as d times of xi star, and similarly ui can be represented as u times of ui star, okay. So, assuming an isothermal flow of Newtonian isotropic fluid, the conservation of mass is essentially very simplified as dui by dxi equal to 0, right. So, we assume an isothermal flow, isothermal being incompressible because there is no variation in density with temperature, etc. All the flow is at a constant temperature. So, this is of a Newtonian fluid, which means again that the shear stress is proportional to the rate of change of velocity with respect to the cross direction, okay. So, du by dy proportional to tau essentially. So, of a Newtonian fluid, and essentially which is also isotropic in nature, okay. So, isotropic in nature means there is no non-homogeneity or inconsistency problem dimensions with the density or viscosity, they are all homogeneous, they are all uniform across the whole medium. So, we assume these three conditions. So, the conservation of mass equation then can be really represented as you saw earlier as dui by dxi equal to 0, okay. So, we try to now represent or put these different quantities here which have been formulated here in, let us say, the set of equations 1. So, we are left with u del ui star by d del xi star equal to 0. In other words, del ui star by del xi star equal to 0. These two being characteristic numbers representing velocity and dimensions, they kind of remain constant, and so they can be taken outside the differential here, and so therefore del ui star by del xi star is 0. So, this is the scale down equation, okay, scale down equation. So, the formulation of the scale down equation in case of conservation of mass is really not very critical. It does not go unchanged, it is just a ratio of the ui star number with respect to the dxi star number again. However, the changes would occur when you look at the Navier-Stokes second conservation of momentum equations, and significant changes would occur which can be interpreted, and some of the properties, essential properties at the micro scale of flows would really come out if you scale down the second equation from Navier-Stokes. So let us do that. So we assume an isothermal flow of isotropic fluid. So the conservation of so we have a so we assume an isothermal flow of homogeneous fluid, an isotropic fluid. Okay. So the conservation of momentum equation as we saw earlier can be represented in terms of if you just go ahead and look into the equation, the momentum equation that we derived before, it was rho del ui by del t, right, plus ui or uj rather del ui by del xj equals rho fi minus del p by del xi plus eta del 2 ui by del xj2. Okay. That is what conservation of momentum equation was really in terms of the notational form. Now if we want to go ahead and substitute the different values of the non-dimensional numbers here, we have again two numbers, as you may just recall, last slide we did this. So xi is d xi star, okay, and all velocities whether it is ui or uj, essentially ui star, similarly uj, we are just talking about a scale. So essentially this is a representative quantity, u is a representative velocity at the particular scale of interest. So whether it is a subscript j or I, whether it is a change in the columnar fashion or the row fashion, the corresponding dimensioned number or non-dimensional number will really not change because of that, and therefore the relationship for j also holds valid. You have this uj as uj star, okay, where uj star is the dimensional number in the or the variation as j varies in the columnar manner, j is equal to 1 2 3. We already talked in details about this notation if you may recall, when we were trying to notate the whole set of the conservation of momentum equations in Navier-Stokes derivation. Okay. So just substituting this back into the equation here, let us say this equation was equation number 2, we are left with a condition where rho times of u del ui star, okay, by del t, we have not yet characterized or we have not yet changed the time dimension, okay, that we will be doing in the next step. So plus we call it u square by d, and this should be equal to really uj star times of del ui star by del xj star, okay. That is how the LHS can be written, and it is equal to rho fi again minus del pressure p by del xi star into d, okay. That is how you characterize this, plus eta, and you call this u divided by square of d, as this notation represents here, it is del xj square. So it is d square times of xj star square with the del, okay. So you have del 2 ui star here, and you have del xj star square here, and what comes out of the equation is eta u by d square. So this kind of clear at the stage what this is about, right. And let us just do a little bit of algebraic manipulation here. We multiply this equation by d square by eta u on both sides, okay. So we are left with now rho d square u by eta u, okay, del ui star by dt del t plus rho ud by eta uj star times of del ui star by del xj star, okay. And here we have del rho d square by eta u fi minus, this is fi, minus del by eta u del p by del x j star plus del 2 u I star by del x j star square. Okay. So, that is how you can write the non-dimensional form of this equation. Although this is not a complete non-dimensional form, again there are certain quantities here I will like to illustrate, like T here, the pressure P here, or the force F here, which is still in the old domain, and you have values here, absolute values of these forces, and somehow we have to develop a mechanism out of whatever parameters we have now to find out if we can really scale down these numbers, okay, or scale down these particular parameters by comparing it to a parameter of same type at that particular scale. Okay. So, let us actually go ahead and transform. So, we will say that this transformation is incomplete because some of the variables, like let us say temperature, pressure, etc., are still not scaled down. All right, and so for that, or for doing that, we would go ahead and actually try to see how we can represent these variables. Okay. Now, for all practical purposes, the only quantity which may differ a little bit is Fi, force which is related to the body force. Now, when we are talking about micro scale flows, the mass of the volumes which flow really are very, very negligible. So, therefore, the whole business about Fi, the body force, okay, is also negligibly small. We can neglect it to 0, and so we need really quantities like T and P to be scaled down in order to ascertain whether we can complete scaling down of the Navier-Stokes equation at the particular scale of reference. So, let us actually figure out what this scale would be. So, T star would definitely be equal to the time in this particular scale T divided by a time equivalent in the scale that we are considering, and we already have the corresponding scaled or scaling parameters for the micro scale of d and u for the length and the velocity respectively. So, d by u definitely would give an idea of what kind of time scales would be appropriate for the scale in question, or for the micro scale at which this equation is being scaled down. And so, therefore, we can represent T star, a quantity which is equal to T by d by u. And similarly, for the pressure, P star can be the ratio between P, and as we know, eta does not vary because eta is actually a scale independent property. It is the viscosity of the fluid, and it is same across all scales, whether it is micro, nano, till it goes, I am sorry, till it goes to a level where continuum is destabilized. Okay. So, but we are talking about the micro scale where we still the continuum holds true, and so neta essentially the viscosity or mu, whatever you call, remains kind of fixed across all these different scales wherever the continuum is still maintained or established. Okay. So, so therefore, this pressure unit, as you know, is same as that of shear stress, and shear stress is nothing but eta u by d. Okay. The rate of change of velocity with respect to the separation distance in the perpendicular direction. Okay. So, therefore, when we are talking about just scaled parameters, it is good to assume u by d times of eta to be the corresponding shear stress which is required for separating such flows or layers of such flows, and therefore, this can be considered equivalent to the kind of pressure scale. Okay. So, P star again becomes P by eta u by d. Now, if I put all these derivations back into our equation here, which we formulated just about a minute back, we will be left with something like, you know, rho u d by eta times of del u I star by del t star plus u j star times of del u I star by del x j star minus you can call it not minus, you can finish the bracket here, equals minus of del p star by del xi star plus del 2 ui star by del xj star, okay, del xj star square. Let me just write this in a little more clearer manner. So this is del p star minus del p star by del xi star plus really del 2 ui star divided by del xj star square, okay. So that is what essentially the relationship would be in a totally scaled down manner. Now you have t star here, note, which is the kind of non-dimensional analog of time t, and you have p star here, which is the non-dimensional analog of p star, and essentially the Fi here, the body forces, which was the term more towards the right hand side here, is neglected because we consider in microscale flows the volumes or the masses involved to be too low for the gravity effects to be significantly affecting the flow. So therefore Fi for all practical purposes in micro scale is 0. But something very interesting has happened in this equation. Let us call it equation 4, okay. So what is interesting here is that this term is nothing but the Reynolds number, the rho u d by n, and this is the kind of characteristic Reynolds number at the scale that you are considering, right, because u d rho and eta of course do not change across these scales till the continuum is established, and u and d are the scaled velocities and the length dimensions at the scale that you are questioning or concerned. So therefore it can be very appropriate to assume that the Reynolds number at the particular scale, I call it RESC times of del ui star by del t star, okay, all these different components of the equation on the left side, del ui star by del xj star is equal to minus del p star by del xi star plus del 2 ui star by del xj star square, okay. Now as we know that the Reynolds number at the scales that we are looking at is really small. It is very less than, I mean almost always less than 100 and very often less than 0.1, okay. Reynolds number is very low, and so therefore the contribution coming from the LHS of this equation is kind of overshadowed by the smallness of the Reynolds number itself, and therefore the LHS vanishes away. You can say that this is very negligibly small and it is 0, and therefore the Navier-Stokes equations finally turn around into minus del p star by del xi star plus del 2 ui star by del xj star square is equal to 0, okay. So this is a very important goal that we have established here, that if you scale down the conservation of momentum equation at the scale of the Reynolds number being very small or micro scale, you immediately find out that the equation becomes time independent, okay, time independent, and therefore there are certain effects and situations in the micro scale which become very prominent where time no longer matters, you know, I mean things like mixing etc. You know, if you just consider mixing by the means of just you know mass transport, that mixing actually becomes insignificant, okay, at the micro scale, just because you know if you have two flows which you are timing in together onto a chip and they go side by side for a little bit, and if you want to reverse them back in time, you should be able to extract the flows as it is back unmixed. So therefore this is a very important conclusion out of scaling down the Reynolds number. So we are towards the end of this particular lecture. I would like to kind of take on from here in the next lecture and try to show you some of the observations and conclusions that we can have from this scaling approach, which essentially starts the domain of microfluidics, and then probably go over some of these fluidic devices like mixers, valves, pumps, etc. in little more details and try to see how they can be applied to biomems platforms. Thank you.